Good day, everyone. Today, we're going to start by reviewing about solutions. We're going to talk about solutes, solvents, the like dissolves like principle, just to kind of get back up to speed. Then we're going to talk about electrolytes, compounds that form ions in solutions. And specifically, we'll be talking about strong acids and strong bases. As a little bit of a roadmap looking ahead where this is going to go, we're going to talk about solutions eventually as we proceed through this unit. We'll talk about acids and bases, what they do, and get into a little bit about reactions. So let's get to it. All right, what is a solution? So recall a solution is a homogeneous mixture of two or more substances, and it has two key components in it. A solute, which is the minor component of the solution, and a solvent, which is the major component of the solution. When water is the major component, when water is the solvent, we call it an aqueous solution. And those are the sort of solutions that we're going to be focusing on in the next couple of units. So recall that solutions can come in all sorts of different exciting combinations. You can have a gas and a gas. For example, air. Air is primarily nitrogen, N2, but thankfully there's a decent amount of oxygen, O2 mixed in, and many, many, many other trace gases, argon, neon, carbon dioxide, methane, etc. A liquid solvent and a gas solute, an example of that is a carbonated beverage. A carbonated beverage is mostly, well, usually water, but if it's carbonated, that means it's got a gas dissolved into it. A liquid solvent with a solid solute is an example of, well, for example, sweetened beverages. So if you dissolve sugar into a liquid, in fact, if we want to get really crazy, we could dissolve sugar and carbon dioxide into water and create soda, or pop, if you will. And then solids, you can dissolve in solids to make a solid alloy. These are just some examples. You can make any combination of solute solvent phases to create a solution. So recall, what happens if we dissolve a salt in water? So remember, the water is attracted to other waters through London dispersion forces, through dipole-dipole interactions, through hydrogen bonding. So it takes energy to be able to break the waters apart. But when they do, and when our salts, in this case we're looking at sodium chloride, NaCl, so remember the ions are attracted to each other through electrostatic potential force. Now, that water can kind of intercalate its way in there and wait for it, wait for it, wait for it, wait for it. There we go. When it's all said and done, energy ends up being released because we form these new favorable interactions. We have the water solvent interacting with the chloride in this case, but you would have the water also interacting with the sodiums, and so you end up getting this. Well, we'll take a closer look at some other depictions of this. So here we have examples of water molecules that are basically swarming around the ions. The partial negative side of water, the oxygen side, is attracted to the positively charged cation, whereas the partial positive side of water, the hydrogen side, is going to be attracted to the negatively charged anions, in this case, chloride. So here we have an example of what a cube of salt dissolving looks like at a microscopic level. So we have our cube of salt, the water comes in, and it basically swarms around the individual ions to create this solvation sphere. So a useful rule that we invoked was this like dissolves like principle. Basically what it states is that molecules that share similar intermolecular forces will generally dissolve well in each other. A generalization, but a very useful one. And the probably most important thing that we got out of that principle is that small polar molecules tend to dissolve in water. Water is small, it's polar, its partial negative end and its partial positive end can interact well with other polar molecules, but it also interacts well with salts. That's what we just looked at. So the partial negative end of water will interact appreciably with the positive charge of an ion, whereas the partial positive end of water will interact with the negative charge, the anion, in a salt. Large nonpolar molecules tend to dissolve better in organic solvents, things like hexanes, large hydrocarbons, or ethers. So we also took a look at the example of oil and vinegar. And if we look at this here, so if we have oil and vinegar, they do not dissolve appreciably in each other. We end up having these two immiscible layers. In layer one, we have the oil, which is mostly carbons and hydrogens. We have these really long hydrocarbon chains in here. Look at them. They don't interact well with water. Water, on the other hand, so water is not going to dissolve appreciably in there, but water will interact nicely with, this is acetic acid. Acetic acid is what gives vinegar its punchy taste. So we can see in here that we have these acetic acid molecules dissolved into this water layer. So this is just kind of the like dissolves like principle in action. A notable example of this principle, for those of you that like hot peppers, those of you who are spice enthusiasts, is capsaicin. So this molecule here is capsaicin. Large, got a lot of hydrogens and carbons in it. And if you've bitten into, say, a habanero pepper or a jalapeno pepper, this is what's causing the tingling or pain of those hot peppers. So if you do that, what is a better solvent for helping to dissolve it out of your mouth and get it off of your tongue? Water, which is, well, water, or milk, which is a combination of, it's got some water, it's got some fats and some proteins in it. Which is going to be better at scooping up that molecule? Well, the answer is milk. Water will afford a temporary relief if your tongue is burning from a hot pepper, but because water is not good at dissolving this large molecule with lots of carbons and hydrogens, it's only going to give that temporary relief from the tingle. Whereas milk, which has fats in it, it has these large proteins in it, like this is casein, I believe, these can help scoop up the capsaicin, which can help remove it from the tongue and can therefore relieve burning. Thanks, capsaicin. Another notable example of where the like dissolves like principle comes into play are vitamins. So vitamins come in two exciting forms. There's water-soluble vitamins, and then there's fat or lipid-soluble ones. Notice how the structures really resonate with this like dissolves like principle. So we have ascorbic acid, vitamin C. Look at all those oxygens and hydrogens, interacts really readily with water. Vitamin B6, small, it's got all these polar groups in it. Vitamin B12, larger molecule, but polarity city, population, vitamin B12. Whereas on the other hand, the fat-soluble vitamins, vitamins A, D, E, and K, those we can't readily find usually in, say, juices and whatnot, things that are water-based. For those, we need to use something that has fat in it because fat will dissolve these. So something like milk, for example, will oftentimes be fortified with vitamins A and D. And we can see here, their structures have a lot more just hydrocarbon character than the water-soluble vitamins. Okay, so before we go on, let's talk a little bit about how we can depict chemical changes. Entering reactions. And reactions, what we do is we write reactants on the left-hand side, we draw an arrow, and then we write out our products. And reactants are what's present initially. They are what are either combining or changing to form the products, and the products are what is eventually formed in a reaction or in a chemical process. The arrow shows us which way this is proceeding. So again, the reactants are what you start with, the products are what you finish with. Turns out not all reactions will continue completely forward. In fact, many don't. And it turns out many go reverse directions. We're not going to really get into that. But some processes are better depicted rather than using a straightforward arrow with a thing called an equilibrium arrow. It's a two-headed arrow. And the reason why it uses the arrows that point both directions is because actually the forward process is occurring and the reverse process is occurring. So in that case, the reaction would look like that. It would have the reactants and the products still written out, but instead of having a full-headed arrow, it would have an equilibrium arrow. Okay, so oftentimes the phase of matter, well, the phase of matter is always important in a chemical process. So there are four key characters that we want to get to know. Solids, so whenever we write a parentheses S after a molecule, that indicates that we have a solid. Liquids, we use a cursive L for that. Gases, we use a G, appropriately enough. And for things that are dissolved in water, we use AQ for aqueous. So if something is dissolved in a water as a solvent, then we're going to use AQ to help signify that. These phases can also be used to help depict, so in this case, this isn't going to be a chemical reaction, but a phase change is a process that occurs. Let's take, for example, the melting of ice. So the way that would look is as follows. We have our H2O that we're starting with in the solid form, and as it melts, it's turning into H2O liquid. So on the right-hand side, we have our product, liquid water. On the left-hand side, we have our reactant, solid water. Okay. All right, so back to salts. What is a key way that we can identify a salt? If you see what two things together, you know, hey, I've got a salt. That's right, if you have a metal and a non-metal. So for the sake of illustrating this, we're going to abbreviate this as MX. So where M is some metal and X is some non-metal or some collection of non-metals. It doesn't have to be just one atom, one ion. And in this unit, and for basically the rest of the course, we're going to say that solids are going to be able to dissolve completely in, or not solids, that salts are going to be able to dissolve completely in water. So in general, the way we would write that reaction out is as follows. We have our salt, we pour it into water, and so as it gets solvated, as the water starts to surround it, it will break apart those interactions and will end up with our metal cation, the positively charged thing, and our non-metal anion, the negatively charged thing. Okay. Now then, electrolytes. What are they? What do they do? So electrolytes are substances that dissociate into ions, that create ions in a solution, therefore allowing the conduction of electricity. Why is it that they allow the conduction of electricity? Well, it's because the flow of electricity relies on having ions. We have to have the movement of charged particles. So if you just have a solution that has no ions in it, it can't conduct electricity. But if you start dissolving ions into, say, water, it can conduct electricity readily. So down here, we have an example of a whole bunch of different solutions. We have deionized water, which has the ions basically removed out of it. We have tap water. Tap water, especially in central Pennsylvania, tends to have a lot of ions in it. It's what we call hard water. More on that later. Then we've got some acids and we've got some bases. They can conduct electricity. So what are acids and bases? Well, for our purposes, we're going to consider what they make in an aqueous solution. Acids, their calling card is they leave H pluses behind. So here's an example of a reaction. We have HCl, hydrochloric acid, reacting with water. So this first reaction that's there is actually what happens. An H plus, a hydrogen from the acid, will actually get physically attached to a water. The water does what's called an attack on it. It's very exciting, really. And it grabs that H plus. So what we end up with then is we have a positively charged, this is called hydronium, H3O plus is one of our products. But we can simplify this. For our purposes, when we look at acids and bases, we can just write out the reaction rather than writing out what it does with water. We can just write the reaction like this. HCl dissociates into H plus and Cl minus. And strong acids, the ones that we're going to be looking at today, dissociate completely. So these are called strong electrolytes because they readily form these ions in aqueous solution. Bases, on the other hand, their calling card is a thing called hydroxide, OH minus. So an example of that is potassium hydroxide, KOH. KOH will dissolve readily in water. In fact, it is a salt, and it'll turn into K plus and OH minus. So now let's get to it. It is important to know the 7 strong acids and how you can identify a strong base. So the 7 strong acids are as follows, and you'll notice that these first 3 have a little bit of a pattern with them. We have HCl, HBr, and HI, so hydrochloric acid, hydrobromic acid, and hydroiodic acid. You don't need to know those names, but you do want to be able to recognize these as being strong acids. So what do these all have in common? Well, it's just hydrogen plus a halogen. So if we look at group 7 in the periodic table, it's HCl, HBr, and HI. And in the words of the great poet and philosopher John Bon Jovi, whoa, we're 3/7 of the way there. The other strong acids are sulfuric acid, H2SO4, nitric acid, HNO3, chloric acid, HClO3, and perchloric acid, HClO4. Strong bases. Well, strong bases actually are just a pattern. It's whenever you have a group 1 metal paired with hydroxide. So it is actually a salt of a group 1 metal and then hydroxide. So we have, for example, LiOH and NaOH and KOH, etc. Or any group 2 metal hydroxide, calcium and below. It's a little bit of a caveat. So if we're looking at the periodic table, once you get to calcium, so calcium, if it exists in water, it's going to have a 2+ charge to it. So it can actually hold 2 hydroxides. So it's going to be CaOH2 because the positive 2 charge needs to be counterbalanced by 2 of the OH minuses. Strontium hydroxide, SrOH2, etc., etc., etc. Barium hydroxide would be another example, so on and so forth. So what is it that makes a strong acid strong and a strong base strong? Well, they dissociate completely in aqueous solutions. So HCl, we're going to use a full-headed arrow. If you have HCl in water, it's going to break apart completely into H+, a hydrogen cation, a proton, if you will, and chloride Cl-. Calcium hydroxide, well, that's also going to dissociate completely into calcium 2+, and it's going to turn into 2 hydroxides. So the calcium is counterbalanced by 2 hydroxides there. In water, all 3 of those ions will break apart into the 1 calcium and the 2 hydroxides. Hydrofluoric acid, as we noted on the previous slide, is not a strong acid. Commonly mistaken, misidentified as one. It's not. So what it does, its dissociation process uses an equilibrium arrow. And the reason why it uses that is because actually only about 1 out of every 1,000 or so of HFs will dissociate into F- and H+, whereas roughly 100% of HCl, CaOH2 are strong acids and strong bases will ionize. So strong acids and bases and strong electrolytes in general essentially create 100% products. They go all the way to completion, all the way to products, whereas weak acids and bases do not. Okay, so strong electrolytes, they dissolve completely in water to form ions. Strong acids, for example, like HNO3, turns into H+ and NO3-. Strong bases, so for example, calcium hydroxide dissociates completely into calcium 2+ and 2 hydroxides. And then the other type of strong electrolyte that you want to be able to recognize, so strong acids are strong electrolytes, strong bases are strong electrolytes, and you want to recognize ionic compounds as strong electrolytes. So anytime you have a metal and a non-metal. So here we have chacuna. This is a molecule called sodium acetate. It's got that metal cation in it, that Na+, and in water it will break apart completely to form Na+ and CH3COO-, also known as acetate. These things are strong electrolytes because when they dissolve, when they turn into ions, they go all out. So here we have our metal cation and our non-metal anion they break apart into. So that concludes this initial discussion about strong electrolytes. Thank you very much for your time. Hope that everybody is doing well, and I look forward to interact with you all soon. Hope you have a great day.